My name is Anna Åberg, and I'm a researcher at Chalmers University of Technology in Gothenburg, Sweden. Today, I will speak to you about one of the world's largest international science collaborations, ITER. ITER is a fusion experiment currently under construction in southern France. And in my case study, I've been looking at the negotiations during the 1990s that went into starting and developing this large-scale scientific experiment. Through the lens of ITER, I will be discussing reciprocity and compromise in science diplomacy. Fusion can, shortly and very simplified, be described as a process of generating energy that happens through the fusion of atoms, as you can see to the left. This is a process similar to the one happening in the Sun and other stars, as opposed to the splitting of atoms, which is the process that happens in our current nuclear power plants today, as you can see to the right. Controlled fusion processes has the potential to produce high amount of energy, and due to this, fusion has over time in many circles been seen as the future of energy and the future of nuclear. This possibility of bringing the sun to Earth, as some try to explain it, as well as the promise of endless energy, has intrigued many scientists, and it has become a part of our political and cultural imagination. Fusion research has also been an arena for international collaborations and science diplomacy since the 1950s, when fusion research was declassified during the Atoms for Peace conferences in Geneva. However, so far, a steady-state fusion process that would generate energy for an economically viable cost has not been developed. ITER is one of the latest attempts to change this. On this picture, you can see the site in Cadarache in southern France, where ITER is currently being built. The ITER project includes the EU through Euratom, Russia, Japan, the US, and South Korea, India, and China. It's thus a very large part of the world's population that is represented in this project. The project is thus very ambitious in its scope, but it also has an ambitious aim: to build knowledge and the ability in fusion field in each of the nations that are involved, while simultaneously constructing a functioning first-of-its-kind reactor. So it's a combination of basic research and industrial development. Building a machine such as ITER is, to say the least, a complicated process, where diplomacy, complex management, and negotiation are at the heart of the project. This is true not only for the top-level politicians who sign agreements regarding scientific collaboration. It's also true for the science policy advisors, scientists, engineers, lawyers, economists, and managers working on the project, all the way down to the worksite itself, where German welders may work under Indian supervision following French nuclear safety protocol. One can say that techno-scientific diplomacy is performed there on a day-to-day basis. In my case study, I've looked at the ways that diplomatic and scientific rationales of compromise and reciprocity are entangled in the process of negotiating a project. I will show you in this talk some ways that the early negotiations of the project continue to influence it today. But first, I would like to say a few words about reciprocity and compromise. The concept of reciprocity has been a core characteristic of diplomacy over time. It concerns the exchange of services or items of equal value. The idea of total reciprocity implies equality in exchange. However, it's important to notice that a lot of the time, negotiation partners are not necessarily of equal standing. In the ITER negotiations, reciprocity, in the sense of everyone getting something out of equal value, was the aim of very many decisions, for example those concerning decision-making power, knowledge sharing and patents, citing of important institutions, and financial gains and losses. The quest for this reciprocity, in turn, meant quite a few compromises. Compromise is another central concept in diplomacy, where it has often been seen as a tool of what one might call a realist mode of diplomacy. What's interesting about the concept of compromise in science diplomacy is that compromise and realism is often seen as something that's specifically inherent to diplomacy, while science, according to the ideals of scientific work, leans more towards idealism, seeking truth, and not compromising with it. This view of science and diplomacy as having very different value systems can also be seen, for example, in central texts on science diplomacy, as for example the one published by the AAS and the Royal Society in 2010. However, if we look at it from a slightly less essentialist vantage point, diplomacy as well as scientific work often have both idealist and realist aspirations, insofar as they can be separated, and both activities may include reciprocity and compromise. In particularly, in a large techno-scientific project such as ITER, decisions need to be based on both the scientific and a diplomatic rationale, and often these two are entangled. I will give you in this talk 3 examples of negotiations of reciprocity that led to compromises in the 90s that has had consequences for the current ITER project. The first one of these is the way that ITER is organized through a decentralized work organization. What you see in this picture is a simplified image of which country manufactures which part of ITER. ITER uses a decentralized in-kind system of organization, where participants contribute by constructing parts of the fusion reactors in their respective countries and then sending them for assembly to Cadarache. Around 85 to 90% of the ITER project funds are constituted of this type of in-kind contribution. This is a particularly high amount of in-kind for a project of this scale, although the in-kind funding is of course used for other projects as well. But what it means is that the ITER machine is almost entirely built in this fashion. These first-of-kind components then that are manufacturers all over the world need to be transported to Cadarache and to be assembled with less than a millimeter precision according to a specific time schedule. As you understand, if only 10 to 15% of the funding for ITER goes to the main site work, this organization is resulting in a network system with a very weak central organization. In practice, this means that the financial power of the project, as well as the full control over procurement and construction, is not necessarily at the central team at the Cadarache site, but is distributed in the national institutions in the different countries. This makes it very difficult for central managers to coordinate. In addition, since the aim is to increase knowledge for all participants, the same component is often built simultaneously by several different parties, as you can see here on the slide, where the flags then represent the different countries who are building the different components. Here we can see, for example, that the vacuum vessel is constructed in both Europe, Korea, and parts in Russia and India, and the same kind of magnetic coil is manufactured in Russia and China, for example. Akko Mas, who is a knowledge management officer at ITER, has commented regarding the construction of the vacuum vessel specifically, that the vacuum vessel is the first safety barrier. If you would ask any scientist, technologist, or safety person what not to do, they will tell you you have to have the vacuum vessel fabricated by one single entity. Yet, as you saw in the previous picture, at ITER it is not. So the question then is, why? This decentralized way of setting the project up has its roots in the early project negotiations in the 1990s. ITER started out as a collaboration between 4 parties: Russia, Japan, the EU, and the US. These were also the countries that then had the most developed fusion programs. At this time, all of these countries had their own plans for a continued national program, and the EU already had an experimental reactor in place. The different parties also had different energy needs and views of the place for fusion in their future energy systems. However, fusion research is resource-heavy, and there was a consensus among the actors that progress in the fusion field could only be achieved through international collaboration. Here, already from the beginning, there is a tension built in between the needs and plans of each country and their politicians and researchers, and the needs and plans for the larger projects. This is, of course, inherent to any international collaboration project. The decentralized model of organization was one way to solve this tension. A more centralized model had been used at the earlier EU fusion collaboration, where parties had given money to a central organization who then held competitive tenders and distributed work. This time, instead, a decentralized model was put forward and was seen as the better choice by several actors, since it would mean less cash flow over borders, in addition to ensuring procurement and influence for each of the national research teams. In addition, to ensure fairness and reciprocity between the parties, a system was put in place that did not require transfer of funds across the participating countries' boundaries. This system would then be independent of exchange rates, labor rates, overhead rates, and other complications. This currency, so to speak, was called the ITER unit of account. So both the way to allocate work in a decentralized way and the ITER unit of account became tools to work for an equal and reciprocal division of labor and benefits between parties who had vastly different labor contexts. So here also the decentralized organization meant to secure exact reciprocity between parties, as well as influence for all scientific groups involved. On the other hand, this then led to a compromise in the form of a less strong central management with less control over the construction process, and this was discussed already from the beginning. This is a problem that has continued to haunt the project over time up until the current situation that Åberg describes in the quote on the earlier screen. This decentralized organization has also been made more complicated within the EU. Although the EU site, which is the Cadarache site, became the main ITER site, the agency that is responsible for the manufacturing and procurement of EU's in-kind contribution to ITER is not at the ITER site. Instead, it is in Spain. The reason for this is that a Spanish site was competing with the Cadarache site as the main ITER site, and when the Spanish site was not chosen, Spain was instead given this agency that coordinates the EU in-kind contribution. In other words, even within the EU, the construction and coordination is not gathered at the ITER site itself. So this is another example of a more recent instance from ITER history when reciprocity and compromise has led to an even more complicated organization than it already was. However, already in the 90s, when I have been following negotiations more closely, siting was also an issue. And then the issue was not where to site the fusion reactor itself, but instead where a joint central team of researchers should be located for the initial research work. At that time, 3 of the 4 original parties, the US, the EU, and Japan, proposed to have the central teams at their own sites. One in the US, in San Diego, one in EU, in Garching, and one in Japan, at Naka. All of these sites were then proposed as the site for this central joint team. And a special group was then given the task to evaluate the different sites, as well as evaluate the possibility to split the central team over several sites. This group came to the conclusion that the best decision would be to gather the joint central team at one single site. Despite this, none of the parties relented, and the final decision was made to spread the so-called central group, which would now be a distributed group, over the 3 different work sites. The 3 here, one in Germany, one in Japan, and one in the US. The fourth party, Russia, who had not proposed a site, instead became the formal site of the ITER Council, who was then cited in Moscow. Thus, reciprocity was ensured here through compromising not only with project management, but also with the scientists' work environment. However, the national research teams also had an interest in ensuring that the scientific work had a close connection to each national research program to legitimize the participation in the project and defend their own research interests. Therefore, there were both diplomatic and scientific reasons for each party to argue for their site. The compromises made with this decentralized organization, as well as the split siting, led to a very complex project setup indeed, which later would lead to a complicated team division with, in the long run, a lot of staffing issues, leadership tensions between the main groups, and a lot of travel between these sites. So I'll remind you that this setup is not for building the machine yet. This is only for developing the model of a future machine. And as you can see, there was now an ITER council seated in Moscow that advised the ITER director and co-director and their administration. There was a joint central team, which was not central, but instead spread out on 3 sites in Germany, Japan, and the US, each with their own deputy director. Each deputy director was chosen from a different country than the work site, so to speak. So the director of the Garching central team was from the US group, an EU representative headed the central team in Naka, and a Russian representative headed the US central team site. The partition of people in the different groups were also meticulously regulated to ensure fairness. Then we have the home teams of each country, each with their own home team leader, as well as 2 technical advisory groups. Adding to this was, of course, a plethora of contacts persons, expert groups, special working groups, special review groups, and specialized research groups, as well as contacts with industry actors and the fusion community at large, and the IAEA, who had also supported the project from the start. The decision-making between all of these groups also held some tensions. The decision-making process also allowed for these tensions because the agreement between the parties emphasized the authority of the director of the whole project, but almost all the other groups emphasized the decision-making process through consensus. So here there was a tension between what might be called a more hierarchical way of organizing decision-making within an industrial project and a more idealist way of making scientific decisions through consensus. As noted earlier, each party had their special interest to defend regarding what ITER should do, depending on national energy policy and research specialties. As an example, for Japan, fusion was perceived as an important technology to help fill an urgent energy need in the country, and their side was thus invested in a machine that would quickly lead to industrial production. Meanwhile, in the US, many researchers were in favor of smaller scale experiments on already existing machines until some of the many unsolved scientific issues were handled, and they did not consider a new type of energy production as urgent. These kinds of competing interests led to conflicts regarding the scientific specifications of ITER. The different views of the characteristics of the machine also affected the size and the cost. During the first year, the machine model grew to large proportions in order to accommodate all the different wishes of the parties. In the end, this proved untenable, and the project had to cut the cost of the design with 50%, thus reducing many of the technical objectives as well. Ever since the start, ITER has been criticized over time for its organizational approach, as well as many delays and lack of efficiency. As late as 2015, an evaluation almost led to the end of the project, before a change in leadership and a revision of the project schedule. Meanwhile, many organizational structures of the early period of the project have remained, including a decentralized model and the current in-kind system. Leadership issues, as well as the management complexity of the geographical split between the home team, ITER institutions, and the ITER site itself, have continued to haunt the project and affect its work. On the other hand, central ITER actors hold that the way the project is set up now is the only way that they could have done it, and that the project would not have been able to materialize in any other way. For example, Bernard Bigot, current Director General of ITER, commented regarding the fact that the EU agency for in-kind contribution is in Spain instead of at the ITER site, that it was a trade-off, but it was the price to pay in order to get out of the situation. And you can see how maybe the wrong decision could be taken, the wrong decision from the point of view of a technical matter. But it's the only way you could make the project move on. This idea that compromise is the only way for the project to survive, is echoed by several members of the ITER leadership. As pointed out by G.S. Lee, earlier Deputy Director General of ITER, they had to do it this way, deliver this way, or not do it. Either one is not very good, but the worst is not doing it. Lee has also pointed out that the way that ITER is built up, despite its shortcomings, in his opinion should be a model for future international work to solve wicked societal and technical problems. And despite many conflicts and parties threatening to leave, and even leaving for a while in the case of the US, it has been suggested, in fact, that the decentralized model, with a high in-kind contribution, seems to have functioned as a kind of lock-in. Parties are more invested in the project when they do not only send money to a central project, but instead ITER is integrated in each home countries in their research and their industry. And ITER is still ongoing and moving forward, with all the parties intact, in an era when international collaboration between many of the involved actors seems like a more and more difficult endeavor due to the geopolitical circumstances. So from a more philosophical point of view, it may be worth asking how much a compromise is worth. And when does a compromise risk compromising, so to speak, a project or its outcomes in the negative sense of the term? So I will leave you with a few take-home messages from my case. First of all, reciprocity and compromise were central to both the organizational and the scientific setup of the project. It was absolutely vital for the project that it was considered fair for all parties on both levels. Fairness and trust built through this perhaps cumbersome frameworks was vital to make parties stay involved. Secondly, science diplomacy and the consequences of it was enacted on all levels of the project, from political to the laboratory level. The compromises influenced everyone working on the project, and many of the scientific and organizational discussions that became the consequences of the decisions had to be dealt with on the floor, so to speak, at the different sites. Also, in the case of ITER, science and diplomacy cannot really be seen as separate entities with fundamentally different sets of values. It may be easy to dismiss some of the solutions as diplomacy trumping science, but many decisions and compromises were made from both the diplomatic and scientific rationale, and even more, mostly these are entangled and cannot be clearly distinguished from one another. One thing, however, is clear. The ITER setup is not logical from the point of view of a project manager, nor is it completely logical from a purely scientific ideal point of view. Instead, the current organizational and the scientific setup of ITER cannot be understood unless it is put in the historical context of science diplomacy. Thank you very much for your attention.